All right, students, welcome to the first of 3 videos for topic 11.1, electromagnetic induction. Just to remind you, this is exclusively a higher level topic. If you're in standard level and you want to sit in on this topic and go a little bit farther with electricity and magnetism, you can, but it's not required, okay? In this video, I'm going to talk about conductors and magnetic fields, like moving wires through magnetic fields, and then I'm going to introduce to you the term flux, magnetic flux in particular, which will sort of lay the groundwork for our discussion of Faraday's law and Lenz's law, okay? And I just want to remind you that essentially in this class, we've essentially studied 2 big things. We've studied statics, which is the situation where things are not moving, and dynamics, which is a situation where things are moving. Dynamics tend to be more interesting because the way that we quantify in physics and mathematics anything changing is something with a time rate of change, or the derivative of some known quantity or known function with respect to time, okay? Now, in the case of electrostatics and electrodynamics, electrostatics dealt with Coulomb's law, okay? So whenever we had a situation where we had static point charges in space, like positive, negative, you know, trying to figure out what's happening between them, that was Coulomb's law. In dynamics, that's the right-hand rule, moving charges, currents, and that sort of thing, okay? One thing you need to know, which I have not talked that much about with you, is that let's consider an electrostatic situation with the Van de Graaff generator. So that was a big hollow metal sphere with charge on the outside. In a situation like that, when charge is not moving, the electric field inside of a conductor is 0, okay? In electrodynamics, however, when things are moving, the electric field inside of a conductor is not 0, okay? And of course that's the case if you think about a wire with a potential difference across the ends. That potential difference creates an electric field in the wire, which is actually parallel to the sides of the wire, okay? Without that electric field, there would be no force to move the negative charge from one end to the other, okay? So that's a very big difference between electrostatics and electrodynamics, okay? And I just want to remind you what we talked about. The right-hand rule applied to moving charges in B fields. It's a cross product, F equals Q times V cross B. Okay, if the charge is negative, then F comes out of the back of your hand, so forth. We also saw in our previous unit, we saw the similarity between south poles and negative charge in terms of B fields and E fields going into those, okay? Remember also F equals BIL sine theta, okay? Which was the magnetic force on a wire of length L, okay? And we talked about the difference between conventional current and real current, okay, or real current. It turns out that in our discussions of Faraday's law and Lenz's law and magnetic flux and flux linkage, whether we're using conventional current or not it turns out to not really be important, and I'll talk about that later, okay? All right, so just here's a quick example. You might want to refer to the handout that I gave you with all of the lecture examples on it and do these examples as usual. Don't just sit there and watch me do it, okay? So example 1, a proton moves past a bar magnet. You should be able to do this no problem at this point. Remember that the magnetic field in this direction, it goes from north to south. So the magnetic field at that point would be towards the right, and using your right-hand rule, because it's a proton, you find that in A, it's into, B, it's 0, and C, it's out of, okay? Okay, now this one's more interesting. I'm going to start example 2 here, and then I'm going to actually continue example 2 later in the next video, okay? So I have a rectangular coil, 20 by 10 centimeters, and I place it in a uniform magnetic field with a known magnitude. So B is parallel to the plane of the coil's area. A conventional current of 2 amps flows in the coil in a clockwise direction. Find the force on sections AB, BC, CD, and DA, okay? All right, so if you use your right-hand rule and everything we've talked about in previous units, you find that the force on AB goes into the page. CD and DA have no force on them because the velocity or the direction of the current is parallel to that of the B field. And then in BC and DA, sorry, those are 0. And then in CD, it actually goes the opposite direction from AB. So the net force on the coil, guess what, is 0. Kind of an interesting problem. Now we're going to revisit this again, like I said, when we talk about magnetic flux, okay? Okay, remember that any charge that's moving is called a current, okay? Now, if we consider a moving wire, length L, moving at a constant V downwards, what's amazing about this is that by virtue of there being relative motion between the wire and the B field, there is then a current that flows through that wire. It's amazing. It's again an example of how you can have a current, an electrical energy, without actually hooking something up to a potential difference source or a battery, okay? Now, each free electron within that wire experiences a magnetic force to the right, and you can use your right-hand rule to figure that out. Now, this magnetic force acts on each electron not because of the current in the wire, it's not a circuit, but because of the relative motion between the rod and the B field, or in other words, the fact that you have a V vector and a B vector that are orthogonal to one another. Okay, so here's sort of a more detailed view of what's going on inside that wire. Okay, so what happens is there's a magnetic force on the electron to the right, okay, which means that you end up having more negative charge on the right side of the rod than the positive side of the rod. That, in effect, creates an electric field inside of this conducting rod, this length of wire, okay? Now, because there's an electric field, there would then be an electric force on the electron going to the left, okay? And remember that the electric field is given by the change in potential difference over the distance, right? You can think about this as being, it's analogous to two parallel plates where the cross-sectional area of each end of the wire could be a plate, like a parallel plate, okay? Now this is V over L because really the distance between the plates, in this case, the ends of the wire, that's L. If you consider the case where the electrons are stationary, okay, the electrons will be stationary when the magnitude of F sub E and F sub B are equal, or in other words, QE equals QVB, or in other words, QV over L substituting in equals QVB. The Q's cancel, and then if you solve for V, which is the potential difference across the ends of the rod, you get that V equals BLV, okay? Now, this delta V is such an important quantity in physics that it has its own name, which is very misleading, okay? You can see that it's a potential difference. It's a voltage, but it's called the induced electromotive force, or EMF, and it has a symbol of a little Greek letter epsilon, okay? This little Greek letter epsilon right here. Whenever you see that, without the naught, it's epsilon. Epsilon naught is different. That's a constant, which we'll talk about later. That's the induced electromotive force, which again, where does it come from? Where does the induced electromotive force come from? The potential difference? By the relative motion of a conductor in a magnetic field, okay? We say that it's induced because it's brought about as a result of motion and things are not touching directly, okay? You also sometimes hear the term motional EMF. Okay, and one more thing, you should be able to show through dimensional analysis that the quantity B times L times V in fact gives you volts. Okay, and that's maybe an exercise we'll do in class if you guys want to. All right. Okay, so example 3. Try this one on your own before you look at my solution. Okay, so I have a 20 centimeter long wire being pushed at a constant speed through a perpendicular B field. What's the induced EMF or the motional EMF? Well, it's BLV, it's 0.2 volts, okay? If this wire were connected to a 2 ohm resistor, what current would flow? Okay, here I'm using Ohm's law where the induced EMF would be the voltage, okay? Remember, E epsilon, motional EMF, induced EMF is equal to the voltage or potential difference. How much energy would be converted to heat in the resistor in 1 second? This is just a very simple circuits problem, okay? How much work would be done? Okay, work done is energy spent, okay? How far would the wire move in 1 second? Okay, and what force would be applied to a wire? You see, so the physics here, we're building upon all the foundations that we laid in this class previously, okay? The only thing that's new here for you is part A. Everything else is very straightforward for you, should be anyway. Now, talking about the concept of magnetic flux, okay, I'm going to introduce the concept of flux to you. And loosely speaking, this term flux refers to a way of quantifying the flow of a physical property in space through a cross-sectional area. And often flux has a rate or a time variation associated with it. In this class, at least initially right now, we're not going to talk about flux being a rate of change of something with respect to time. We're going to keep it a little bit simpler than that. But loosely speaking, it's this. So if you look at this diagram, okay, you see I have a quantity that goes from left to right, depicted by vectors. It could be a vector field, could be a B field, could be a force field, could be any sort of thing, okay? If I want to quantify the number of field lines that go through a cross-sectional area, which are here indicated as purple vectors, right? The flux is simply a way of mathematically quantifying that, okay? And flux is the number of field lines or amount of something per unit area. And like I said, it's often per unit time, but we're not going to consider time right now. So some examples, which are not as rates, that we use in physics, there's millions of examples of flux. There's momentum flux, heat flux, volumetric, mass, energy, particle, okay? And you can see that all the units of these fluxes, they're all something per meter squared, per unit area squared, okay? Now there's a very important thing that we have to consider here, all right? The angle between the quantity, the field, and the area is crucial, okay? So, for example, in this particular case, if this little pad represents the cross-sectional area of the loop, okay, all right, you can see that if the loop is perpendicular to the field, I'm going to get a maximum flux, right, okay? If it is parallel to the field, I will get zero flux because there will be zero field lines going through it, okay? So the angle is absolutely crucial here. In this example right here, I have an example of it looks like a force field. You see how the field is not uniform throughout this cross-sectional area, which is depicted by this big green square here, okay? We're going to deal with constant fields in this class to keep it easy. Later, if you take physics and or mathematics when you go to university, you'll deal with this case where you have a varying field, and you'll be using calculus for that, okay? Turns out that only the perpendicular components of the cross-sectional area and the field or the quantity are the ones that matter. And to do this, what we have to do is we have to use a mathematical product. Now, you might think that it's going to be a cross product, but we actually don't use the cross product. Because the way that we quantify area as a direction is we have the cross-sectional area times the unit normal vector, if you remember that from last time, okay? So this little diagram over here takes one infinitesimally small square, and we're calling that dA. And so dA is an infinitesimally small square. It is actually the actual area of that little square times the unit normal vector. That being the case, we can quantify the angle between this little dA vector and the force at that point with an angle of theta, and we can see that flux, because it depends, it's the multiplication of the two perpendicular components, it's actually a dot product here, okay? So the flux is going to be F dA times cosine theta, okay? All right, so if the two, the dot product, what this means is that if the two are perfectly parallel, you're going to get a maximum flux, which is what I said before with the field lines going through the varying angle of the loop, okay? If the two are parallel, you're going to get zero flux, which is correct physically. Intuitively, you should be able to get that, okay? Now, formally speaking, the magnetic flux, which is what we're going to focus on here, is the amount of a magnetic field going perpendicularly through a cross-sectional area in space, okay? It's also sometimes called flux density, okay? And there's this very special, there's a very special equation for this, okay? It's that phi, this is the upper Greek letter phi, which always signifies magnetic flux, okay? It's the dot product of B and the cross-sectional area, which of course is BA cosine theta. Now, when everything is orthogonal, you don't have to worry about the cosine theta term. We're going to worry about it. We're going to talk about that cosine theta term because it turns out that the variation in angle between the plane of the coil and the B field has huge implications in terms of the application of all this, in terms of generating electricity, okay? And again, theta is the angle between the magnetic field and the unit normal vector. The units of flux, as you can see, are Tesla meter squared. It's not Tesla per meter squared, it's a Tesla meter squared. And this is called a Weber or a Weber in physics, okay? Now, you can look at different cross-sectional areas here. I have a very simple situation here where I have a garden hose and I have water coming out, right? If I orient different loops of different sizes and different orientations, you can see that the amount of water that passes through each loop is quite different, right? You're going to get the maximum water going through a loop in the first case right here, right? If I have a smaller loop, I have less flux because now A goes down. if I have it tilted at an angle, right? Like for example, this one right here, there would be no water going through it, right? So that's my theta term there, okay? If I have more than one loop, okay, or more than one cross-sectional area, it makes sense that the magnetic flux would be the addition of all of those individual loops. And in fact, the total flux would be n times BA cosine theta. And this has a special term in physics, and it's called the flux linkage, okay? As an example, in this case, I have a cross-sectional area, which is 1 by 3 centimeters. And in this case, I have 9 B field lines going through one surface area. And the area is 3 square centimeters. If each blue vector represents 1 Tesla, and if this angle right here is pi over 6, then it turns out that the total magnetic flux through that would be 21 times 10 to the minus 3 Webers, okay? And you can check my math on that. Notice that I am using radians and not degrees here, okay? Very important diagram here for you guys to understand, okay? All right, now we're going to continue number 2, which is the one that we started earlier in this video, okay? All right, so for part C, this was the one with the coil that was free to rotate in a magnetic field, okay? The magnetic flux through the coil would obviously be 0 because the plane of the area of the coil is exactly perpendicular to the B field. Now, if the coil is rotated by an angle of pi over 2, what is the flux through the coil? This condition would give the maximum magnetic flux, okay? So the cosine of theta would be 1, because theta would be 0, okay? And this ends up being 0.001 Webers, okay? E is the most interesting part of this problem. It's saying sketch a graph of magnetic flux against the angle theta as theta is increased from 0 to pi over 2, okay? From 0 to pi over 2, okay? Well, at 0, the two are parallel, so that's a maximum. That's what I just found right here. That's BA, which is 0.0010 Webers, okay? At pi over 2, it's 0. And in fact, what it does is it goes down like this, and this ends up being 1/4 of a wavelength of a cosine curve, interestingly. Maybe not surprisingly, maybe surprising.